Okay, hello everyone. Today we'll be discussing the next section, which is section 5.4, titled Elastic Stress Strain Relations. And we'll now be actually developing the stress strain relationships for a truly three-dimensional case in which you have all the components of stress and all the components of strain. So that is what we intend to do in this particular chapter. So let's try to motivate this first. As is mentioned by the author in your textbook, in the preceding sections, stress-strain relations were considered for the special case of uni-axial loading. Okay, so if you recall the previous classes of this chapter, we have only referred to this one-dimensional case, uni-axial case, and we did a tensile test at the start of it to be able to draw graphs and then idealize those graphs and eventually learn about plasticity. Okay. Now, only one component of stress, the axial normal component, was present, and only the axial normal component of strain was considered, sigma x and Ex, if you recall. In this section, we would generalize the elastic behavior in the tension test to arrive at relations which connect all 6 components of stress with all 6 components of elastic strain. Okay, so why 6 components of stress and strain? Because the 3 of them are actually the same because of the symmetry of the stress and strain tensors. Okay, the shear terms were same, like sigma xy was the same as sigma yx, tau yz was the same as tau zy. Okay, so we will also restrict ourselves to materials which are linearly elastic, so that corresponds to this behavior. This one 5.7b, this one. Okay, so the stress will linearly depend on strain, and one question which comes up is that in a three-dimensional situation, what does it mean to have a linear stress strain relationship? I mean, there are 6 components of stress and 6 components of strain. What it would mean that the components of stress are linearly dependent on the components of strain. So mathematically, this means that every component of stress is linearly related to every other component of strain. So I will give you one example. Sigma x will be equal to C1 epsilon x plus C2 epsilon y plus C3 epsilon z plus C4 epsilon gamma xy plus C5 gamma yz plus C6 gamma zx. Okay, sigma y will be related to every other component. Okay, and so on. So same would happen for say sigma xy. It would be say related to f1 ex plus f2 ex plus f3 ex plus f4 gamma xy plus these other two more terms. So this is the meaning in a three-dimensional case. What does linear elasticity mean? That every component of stress is linearly related to every component of the strain, and the reverse will also be true in the sense Ex will be equal to L1 sigma 1 plus L2 sigma 2 plus L3 sigma 3 plus L4 sigma xy plus L5 sigma xz plus L6 sigma zy. Okay, so that is what we mean in this. So this is mathematically the definition of a linear dependency, and again you must have learnt about it in your maths courses where you studied linear algebra. You would know how to solve these equations as well, right? Using the Gauss point method, you pivot an element and you exchange rows. Okay. So all those things you should have learned by now. Anyways, so we'll restrict ourselves to the materials which are linearly elastic, corresponding to the idealized model of figure 5.7b, which we have just seen. we shall use our definition of strains, the one developed in section 4.10 and expressed in 4.33. So for example, E epsilon x would be equal to dou u by dou x, epsilon y would be dou v by dou y, gamma of xy will be dou u by dou x plus dou y by dou v by dou y, and so on. Okay, so we have seen that in equation 4.33. If you doubt it, please go back and see what equation 4.33 is. Okay, so clearly when we derived these definitions of strains, we had pointed out that the strains are small compared to 1. Okay, so that is why it was a small strain theory. Okay, so this assumption of taking a linear elasticity works well for many cases, even for say steels. Okay, even for a material like steel, which you, so let's see if we can have a steel, or metals for in general, I mean. Okay, so I mean, when the strains are small, even though this overall stress versus strain graph is non-linear, but when the strains are small, you can assume, like in this region, you can assume linear elasticity to be valid. And that is why we say for small strains we will be using linear elasticity for all materials, except some materials which are highly non-linear. Okay, like even from the start they don't start showing any sort of a linear approximation. So it's materials like say rubber. Okay, so there is a large non-linear elastic strain present, so we cannot make that approximation over there. But for most other materials, linear elasticity works good enough if the strains are small. Even in the materials like steel, if the strains are large, then we cannot assume linear elasticity, and we have seen the figure uh, in this chapter itself. Okay, for larger strains there is no linearity. Okay, so let's also study some of the physical aspects of materials. I mean, this is again sort of juggling between what you learn in material science and in this course, but we'll just go through some parts of it which I think are necessary. So all solids have some regularity in the arrangement of atoms of which they are composed. Okay. Now what this means is, if you recall from your material science course, there are these FCC, BCC, HCP sort of, okay, unit cell structures where there is a fixed arrangement of atoms. So for many metals this is the case. If I recall correctly, I think iron is FCC or BCC. Well, I mean, you would know better than me. Okay, so you should know that the pure iron is of which crystal size. So that is what they say, that all solids have some regularity in the arrangement of atoms of which they are composed. Now, one extreme case of this regularity is the metals have atoms arranged in a regular crystal lattice, and plastics consist of long molecules of chain. So if you see the plastic material, they will have some sort of a molecular structure, but it would still be a regular structure. Okay, I mean, it's not random even in plastic materials. For glass, I mean, for example, glass is essentially SiO2 in the tetrahedral form. Okay, so this also has regular structure, so called. I mean, the atoms are arranged in somewhat a regular fashion. Okay, now these structure elements have different stiffnesses in different directions. That would be obvious because the atoms are arranged in a specific way. So if you try to pull an atom in one direction, I mean, consider this case in which you have 1, 2, 3, 4 atoms. Okay, now you are trying to pull this atom in this direction by a same given force. Now consider another configuration. It's an hypothetical configuration, but you will very easily relate to the structures which you learn in material science. Suppose you have two more atoms in this way. Okay, so clearly the deformation which you would cause along this direction in this case, okay, will be different than the deformation which you would cause in this direction for the same amount of force, just because there are these two extra atoms present. Okay, so along different directions they will have different orientations, and this particular atom, if you try to say, I mean in this case, rather than not doing this, you apply a F by 2 and F by 2. Okay, clearly the behavior in this direction will be different than the behavior in this direction. So this is called anisotropy. Okay, and they have different stiffnesses along the so stiffness, as you know, is just the ratio between the force and the deformation which you have had. Okay, so they have different stiffnesses in different directions. In many materials, these structural elements are arranged in a random fashion and are so small that there are millions of them, sometimes billions in a cubic inch. Okay, so when you have this random arrangement of atoms which is not regular, okay, then there are lots of them in a small volume which is cubic inch given in your textbook. Now even a cube of such a material which appears small to the naked eye will have thousands of structural elements with just about every conceivable orientation relative to the axis of the cube. Okay, so I mean in a random structure you will have atoms in not so much in a regular way. So they will have all these possibilities inside this small cube which you see with your naked eye. Okay. So just to tell you that the scale at which I have drawn these two figures is at an atomic scale, but the scale with which I am drawing this is a broader scale, a larger scale. So that's why I show all these atoms inside it arranged randomly. Okay, now it just so happens if these orientations of these atoms, I mean these small orientations, like for example, if you take a small combination like this may have an orientation like this. Okay, if you take another small orientation, some small collection of atoms somewhere, they may have an orientation like this. Okay, just because those 3, 4 or 5 atoms which you are considering, they may have aligned themselves like this. Here it was very clear how they have aligned. Okay, but in a random solid, I mean, and you know that if this is a unit cell, the same idea will keep on propagating. So the above it you will have the same situation, on the side of it you will have the same situation. Okay, so that would be there. Now in this randomly placed configuration, you will have all of these possibilities of orientations, and two cubes, and if the then two cubes cut out of materials at different angles will have the same statistical distribution of orientations of the structural elements relative to the cube axis as shown in figure 5.12. So if you look at 5.12, okay, the idea is this, that if you cut out one cube of this randomly arranged atom, sorry, randomly arranged configuration of atoms, and they have all these, I mean if you recall from material science, these things are actually grains. Okay, and the boundaries which you see over here are the grain boundaries. So you can see by the orientation of the lines that they are of this orientation, this one is of this orientation, and so on. Okay, now the idea is that if you cut out two pieces of cubes from it, say one like this, the other like this, overall they will not have a preference along any direction. Meaning if you want to apply a force on one of these parts which will have some sort of a random structure like this, grain structures over the orientations, and the same will happen say in this particular direction for the same cube, you will not see a difference in the behavior. The stiffness will come out to be the same no matter in which direction you apply your force. So this is called a isotropic behavior. When there is no difference in the mechanical behavior of a solid along various directions. Okay, so this is how you can macroscopically understand and from the ideas of material science. So most of the metal alloys which you consider, alloys, not the metals, pure metals themselves, they are by and large considered isotropic because they do not have a very regular structure of atoms which goes on for a longer length scale. Okay. Okay, so before we move ahead, I'll give you one other small example so that you can understand anisotropy and isotropy in a much better way. Okay, so consider this situation. I mean, it's something which you can perhaps do at your homes. Okay, go to your kitchen and put a foam. I mean, say a foam with which you clean dishes at your home. Okay, those dishwasher foams. Then you put a steel plate. Okay, put another piece of foam. Okay, put another piece of steel. Okay, perhaps the same plate which you have put before. Okay, so now do this experiment and you can do it at your home right away. I mean, try to align this to a wall. Okay, so this must be a wall or any fixed sort of surface. The idea is that it should not, this should not move in this direction. Okay, I mean we are constraining the motion. So this is a wall, this is perhaps a table, okay, or your platform in the kitchen, whatever works. Okay, so you have steel, you have foam, you have steel, you have foam. Now apply a force F whatever way you can. I mean, one easy way is to say keep your mobile phone or something, some a weight which is which you know is which you know somewhere about, or even by your hand you can do this. I mean, apply a small force and note down how much this has moved down. Okay, delta V vertically. Okay, so this is the first thing which you should do, delta V, which you should note down, and you know that the stiffness of it can be in the vertical direction as force by delta V. You want to convert it to stress, well, you can just divide this by the area and this by the original length, this original length, you will get the strain. So we are not doing that, but you can easily do that in this case. Okay, now repeat, now remove this force. Oh, I'm sorry, it should be foam, steel, foam, steel. Okay, now remove this force and this time apply this force over this particular surface. Okay, now second case is when you measure, and you have to apply it as a stress so that it's uniformly applied over this entire thing, maybe through with a plate or something like that. And this horizontal displacement you should note as delta H. The stiffness will be equal to F by delta H. Now, can you tell, I mean, after having done this experiment, will delta V be smaller than delta H? In this case, when you have a foam, steel, or will delta V be greater than delta H? Well, you would know that the vertical deformation will be larger than the horizontal one because of the way the steel is arranged over here. So this is what would happen, and because of this, the stiffness of the in the vertical direction is smaller than the stiffness in the horizontal direction. This is what is anisotropy. Okay, so this is what is anisotropy, and you would want to clearly understand this concept right away, because the behavior which you have measured through stiffness is different along different directions. It is called anisotropy, and if you had somehow found out that along all possible directions you would have the same stiffness, that would be an isotropic case. I mean, you consider a tennis ball. Okay, now you apply a force like this, or you apply a force like this. You will observe that there is the deformation which will happen will be the same along any direction. Okay, any direction you take, the deformation along that direction will be same. So this means that the stiffness along that direction will be the same, and hence you don't have to worry too much about the direction. So this is called isotropic behavior. Now the word anisotropic and isotropic is not limited to the mechanical behavior alone. It can be there for any material or any other property. Now look at this material, okay, and consider a property like electrical conductivity. It may just happen that this material conducts electricity or heat more in this direction, but as soon as you try to conduct electricity or heat in this direction, it is quite less. So this becomes anisotropic in electrical conductivity. Okay, look at the optical properties also. So electrical or thermal we have just discussed. Look at the optical properties. Maybe there is a material which allows light to pass freely in this direction. I mean, the intensity, for example, does not change a lot. But if you try to pass the light in this direction or this direction, the intensity reduces drastically. So this is anisotropic in the optical property of a material. Okay, so this word isotropy and anisotropy is not limited to mechanical properties or mechanics as such. So this is something which you will keep in mind. But of course, I mean, we'll only concern ourselves with this particular behavior of a mechanical behavior. And you have seen the reason why isotropy exists. I mean, just because the atoms are arranged in a random fashion, they do not have a preferred direction if you collect a few of those structures. So structures in this diagram is the grains, okay, but there are many other structures which are possible depending on the kinds of materials which you have. So we have not given it a name specifically over here. Okay, now let's move ahead and say this. Okay, let me just remove this part. So the general state of stress is described, I mean, if you remember, the general state of stress is described by three normal components of stress and three shear components of stress. The idea is that if you know these 6 values of stress at a point, you will be able to find the stress vector or tensor along any orientation. Okay, so it need not be the Cartesian orientation. Even when you rotate it by a certain angle, we have done that. Okay, so that is what the state of stress is. 6 normal and 6 shear components, and the same applies for strains as well. The most general state is because you have 3 normal strain components and 3 shear strain components, and you can again apply Morse circle transformation in both of these cases to find the stress or strains along any other orientation which is not aligned to the Cartesian plane which we had taken originally. Okay, so that was, if you remember, a plane which was aligned at an orientation n, and that makes an angle theta with the original axis. So we have done all those calculations and derivations. Okay, so we'll consider various components of stress one at a time, and add all their strain effects to get the resulting strain in the presence of all components of stress for a material which is assumed to be isotropic. So we will only proceed with an isotropic material in this course. If there is time permitting towards the end of this course, I will discuss anisotropic with you, and that would lead us to composites like a bone or a wood, which I have given you example. I mean, the fibers are arranged in a direction, so the stiffness along those fibers will be larger compared to, say, a direction which is perpendicular to those fibers. So that is something which we'll see, time permitting, towards the end of this course. We will not discuss them right away. Okay, so for an isotropic material is what we'll be restricting, and we'll take various components of stress one at a time, and then we'll keep on adding the strain effects. Okay, so let's work towards that. So the first step is to consider an element on which there is only one component of normal stress acting. Look at this diagram, figure 5.13. Okay, so you have only one component of stress which is acting over here, and that is sigma x. The directions are shown to you. As discussed in the previous section on the tensile test, this normal component of stress will produce a corresponding normal strain, which was epsilon x, and you are only considering direction stress versus strain linear relationship. So Ex epsilon x will be equal to sigma x by E. Okay, so as I've said, you take one step at a time, and this is the first step. So this is the form of Hooke's law for a uniaxial loading, and we had first discussed this in section 2.2. If you go back to section 2.2 right now, you will recall why this is the Hooke's law. Okay, and I mean, just the definitions will be slightly more expanded over there, because we didn't actually introduce the term stress and strain by that time. Okay, so because the strains will be seen as deformations divided by the length L, and force, the sigma x stress will be seen as force divided by the area A. So force will be P divided by area A. So that is something which you can see. And the modulus of elasticity E is numerically equal to the slope of the line 5.7b. So 5.7b, if you go along over here, the slope of this is E. Okay, so not the angle. So this is sorry, this angle, if you want to denote, that would be tan inverse E. Okay, so that is what is linear elastic isotropic solid, and you have considered only one component of stress right now. Now, since we want to develop a general theory in which not just the one component acts, I mean, you can have forces or stresses acting in all the directions. So, you want to say, in addition to the normal component of strain in the x direction, our experience with rubber bands, if nothing else, leads us to expect that there will be a lateral contraction when a bar is elongated, right? When you elongate any piece of rubber band, you may have seen, though it increases in length, it decreases in thickness. So there is a lateral contraction when this bar is elongated. And we had seen in this tensile test also that how you can use a strain gauge to measure not just the elongation along the loading, but also the compression along the lateral directions. Okay, so there are ways to measure this change. So that is What when they say detailed measurements made during the tensile test bear out this supposition, and lateral compressive strain is found to be a fixed fraction of the longitudinal extensional strain. Okay, so when you do this test, let me just come back to this one. Over here. Okay, when you conduct this test, so this is how you measure the longitudinal sort of extension. Okay, it will extend in this direction, but it will contract in this direction. This both these things you will be able to measure. Now it just so happens that contraction and this contraction and this extension is actually a fixed ratio. The ratio between this contraction and this extension is fixed for a material. Okay, and this is called as the Poisson's ratio, shown by this symbol nu. Okay, so this is there, and this is again specific for the material. It is not dependent on the size of your dimensions of your specimen. Okay, so the contraction which you have in length divided by the extension which you have in the longitudinal direction, the contraction in the lateral direction and the extension in the longitudinal direction, the ratio is fixed, and that ratio is called Poisson's ratio. Okay, so let's come back over here. Okay, so the lateral strains in this particular case, so the longitudinal strain is E epsilon x, the lateral strains are epsilon y and epsilon z. Okay, so one of the things about this particular test is that this will be same. Reason is that the material is isotropic, so there is no reason for it to contract, say, less in the y direction and more in the z direction because of the way you are applying this loading. So this will not distinguish between y and z directions during contraction. Hence they will contract equally. This cube will contract equally. The strain will be same. And okay, so once that is figured out, you can write epsilon y is equal to epsilon z. And oh, I'm sorry, I should make one correction over here. So when I said this contraction and the extension ratios is fixed, it is actually the normalized contraction and the normalized expansion. Okay, what I mean is that this C has to be divided by this dimension, the original one. So I'll put a C star, and this extension over here has to be divided by the original length, which is the gauge length L. So then it would not depend on the dimensions. Okay, this is one correction which you should note. Okay, so that is why, and this, as you know, is the strain in this direction, and this would be the strain, normal strain in the x direction. So that ratio is written as nu, and okay, so epsilon y is the same as epsilon z for the reasons we have discussed, and this is a ratio minus nu epsilon x. So we have already discussed about the Poisson's ratio, and we know about why this is a fixed value. Now why this negative sign? The negative sign actually indicates that whatever be the sign of Ex, epsilon x, epsilon y and all epsilon z will be of a negative sign to that. For example, if epsilon x is positive, that would mean there is a extension in the x direction, but there is a contraction in the y and z direction, and that you can see in this diagram also. Similarly, if epsilon x has a compression, then this would be negative, and with this negative sign these two would become positive. That would mean there is an extension along the y and z directions. Okay, so I'll write minus nu, and this I will take up from over here, which is the Hooke's law, and that would make it sigma x by E. Okay, so that is what we meant by taking one stress component at a time and then finding out all the associated strains with it. Okay, so that is this particular stress, only one sigma x gives rise to these values: epsilon x, epsilon y, and epsilon z, the three strain values, and you have found that out. Now we would consider the possibility of the shear strains resulting. So we have taken care of, I mean, remember there is one strain sigma x, and what are the possible one stress sigma x, and what are the possible strains? Sigma epsilon x, epsilon y, epsilon z. Then you would have a gamma xy, gamma xz, gamma yz. Okay, so we have taken care of these three for now, and remember they have, all of them are linearly related to sigma x. So sigma x is equal to c1 epsilon x plus c2 epsilon y plus c3 epsilon z plus c4 gamma xy plus c5 gamma xz plus c6 gamma yz. So we are still to find out what happens to them for this case. Now consider the possibility of a shear strain resulting from the normal stress sigma x. We want to see now how this can be calculated. Now the isotropy of the material simplifies the relations, and let's see how. Suppose, I mean, let's look at this. Okay, suppose that a shear strain were present, okay, because of the action of sigma x alone. Okay, because of the action of sigma x alone, consider that shear strain is present. Okay, and that is shown in this figure 5.4a. You know what a shear strain is. For the shear strain to happen, there has to be a certain rotation in this volumenar element. Okay, it's not exactly a cube. If I have mistakenly said that anywhere, please ignore it. We don't want this to be a cube. It can, I mean, these dimensions can be of a different size. It's rectangular definitely in the angles, but it need not be a cube. The reason we are dealing with strains, right, that the strains take care of all the other dimensions even when they are different from each other. Okay, now if there is a shear strain present, then there has to be a rotation in this element, and that is shown by these dashed lines over there, and you can see how that happens. I mean, if you recall, if this was your original sort of O and I don't know C and E, you would call them a shear strain when this would move to O dash, this would move to E dash, and this would move to C dash. So the element would now look like this, and the change in this angle from 90 degrees to this is what we called as the shear strain. So we are doing the same over here in a three-dimensional case. Okay, so we want to measure certain angles and see how that happens. But for that we must first cause a rotation, a relative rotation between two edges which were originally at 90 degrees to each other. Okay, so let's assume that a shear strain is present. Okay, I'll just rub this part out, as is shown in figure 5.4a. Now, if you rotate this element by 180 degrees, you will get B. So let's first see that this rotation has indeed happened. So A has gone up over here. Okay, so this is the axis of rotation, so you can clearly see how this axis of rotation has happened. Okay, how this rotation has, it has rotated about the x-axis. So A has gone up there, F should have come over here from there, D should have gone from here to here, E would have gone from, sorry, E should have gone to this place, so this is E, and C should have gone, so this is C. Okay, please make this correction, this is C over there. Okay, so you have caused this rotation, and since the this this protruding part which was there in A should have now moved over here, right? Because just because of how all the points are moving. I mean, the idea was that this B would have moved to B dash, and hence this B would have moved to B dash, right? Just by this rotation which was happening. Now this would give a shear strain in the opposite sense. So the sense of shear strain was like this over here, but the sense of shear strain in this for the same sigma x, you see the direction of sigma x is not changing on this solid element. Okay, so you have a different sense of shear strain. But there is the problem. If the material is isotropic, which it is, which we are assuming for this entire course as such, the mechanical response to the same stress on this volume should not be different. Meaning, for the same applied stress after rotation about 180 degrees, you cannot have this deformation acting in an opposite sense. So you should have had a deformation in the same sense because it's an isotropic material. Okay, so this contradiction which you get right now can be only avoided if you say that there is no shear strain. Now this argument we have used in a simplistic way at least one time before in this course. Please go back to this course and dig up your chapter 1, 2 and 3 to see. This was related to forces then, okay, and we concluded, well, because of this has to happen and that has to happen and both of them cannot happen at the same time, so the only possibility is that this is equal to 0. The same is happening over here. You cannot have shear strains of opposite senses for the same applied loading, which is the stress over here. So this contradiction is avoided only if the shear strain due to normal stress component vanishes. And a similar argument would show that the other two components of the normal strain. So which was this component, by the way, can you recall? It was on the y plane in the z direction, right? Yes. So it was a gamma yz, this particular strain. Okay, and you can use the same argument for the other two strains as well, in the sense then you must apply, say, a load over here in this sigma y direction, and then consider the strain in the xz plane, and then you would find that to be 0. Okay, so that would mean the shear strains are all 0 because of the action of a normal stress only. So that's one part which is made easy. So sigma x, which was supposed to be equal to C1 epsilon x plus C2 epsilon y plus C3 epsilon z plus C4 gamma xy plus C5 gamma yz plus C6 gamma xz. These terms are all 0. So you are left out with this only. Okay. Okay, so that's the first stress which we have, one stress component which we have already dealt with. Now we'll go back to, the paragraph which is above figure 5.13 in your textbook. Before the paragraph which begins with the general state of stress. And I will go through the method which we are following to get the stress strain relations again. I'll repeat it again. We shall consider the various components of stress one at a time and add all their strain effects to get the resulting strain in the presence of all components of stress for a material which is assumed to be isotropic. Okay, so this was just one case in which we have found all possible strains. Now we must uh, get all the stress possibilities one at a time and find the corresponding strains, and eventually we will add them up. So you will see that happening next. Okay, so if you now consider second normal component of stress, I'm sorry, over here there is one minor correction. When I said using same arguments you can prove that the other strain components are 0, you have to continue applying a sigma x only. Okay, you cannot change sigma x. I had mistakenly told you that you can apply sigma y. No, you have to continue applying sigma x, and then you have to assume that there is a strain, say in this direction, that this part has gone up, something like this. Okay, and then using the same arguments you would rotate it by 180 degrees and say that the sense of the, if you rotate this by 180 degrees, it will come down like this, and the sense cannot be opposite for an isotropic solid for the same applied load or stress. You would have to suffice with saying that the shear strains are 0. So that's one correction I should have made. So please go through this once carefully to understand it. Now you apply the second normal component of stress, which is sigma y. Okay, and sigma x is gone. Only sigma y acts now. And because of the linearity of the stress strain relation, an increment of stress will always produce the same increment of strain regardless of the level of stress before the increment was added. Now this is one thing which is there. Then let me just say this carefully. What sigma y will produce alone, okay, it will produce lots of things. It will produce an epsilon x. It will